Right, okay, so the harmonic oscillator. So the harmonic oscillator is the simplest systems in physics. You have an oscillator, you have something back, forward, back, forward, back, forward, oscillating at a certain frequency, omega. And those of you in second year and above will know, and those of you in the first year, I am going to ask you to accept that when the harmonic oscillator is described using quantum mechanics, whereas in classical mechanics you have there's an infinite possible amount of amplitude, there's an infinite possible amount of energy, that you can have any possible value for the energy in a harmonic oscillator. In quantum mechanics, the spectrum becomes discrete. The spectrum is quantum, it is quantized, it is discrete. So in the quantum system, the possible energies are n plus a half h omega. And the lowest lying state is the ground state. The ground state does not have zero energy. The ground state has a finite amount of energy, h bar omega O2. So associated in quantum mechanics to the vacuum, to the lowest possible state you can have, then in quantum mechanics there is energy. The energy is not zero. There is in a quantum harmonic oscillator, the lowest lying state you can have, the ground state, has a finite energy associated to it. Why does it have a finite energy associated to it? So again, you can calculate it, but there's an intuition for this, and all of you, all of you, I mean, even those in the first year, ought to be able to understand why a quantum harmonic oscillator has to have some energy in the ground state, as long as you can accept the uncertainty principle. So the uncertainty principle, so I'll use the, I won't give them precise, I just use the sort of sin signs for other way round. I'll just use sin signs here, so I'm not going to get into language that Rasen gets here. So the uncertainty principle is the idea the uncertainty in the position times the uncertainty in the momentum has to be bigger than a certain amount, roughly h bar. Why does this mean that the ground state has to have a certain amount of energy? So recall what the two types of energy you have. You have kinetic energy and you have potential energy. So you have kinetic energy, p squared over 2m, and the potential energy of half k x squared. So what happens if you try to localize the, so you might reduce its potential energy to zero by localizing it precisely at the origin, then the uncertainty principle tells you that it's got to have quite a bit of momentum. So it will have lots of kinetic energy. If you try and reduce the kinetic energy to zero and take p down to zero, then you will find that this thing has got to be spread out in position, and so because it's spread out in position, it's got to have its experiences high up on the potential, and so it's got to have potential energy. So the uncertainty principle is then the kind of physics reason why the ground state of the harmonic oscillator, the lowest line configuration of the quantum harmonic oscillator, has to have a finite amount of energy. And the uncertainty principle, as you know, is associated to Heisenberg, the German physicist. You may not know. So, you know, Heisenberg was born around 1900. You may not know that at the kind of the same sort of age you are right now, while you were a student. So there was, after the First World War, there was a kind of a mini German civil war between the kind of the whites and the reds. And around the age you were, Heisenberg had to, most nights, had to kind of creep out across the front lines in this in order to get food for his family from a nearby farmhouse. So, yeah. An experience probably most of you do not have right now. But let's come to the uncertainty principle. So, what is the uncertainty principle? What does it say? A particle, a fermion or boson, is measured to pin down two facts which ought, by sense, be knowable. How fast it goes and where it is. Dream. Invent. Deploy all thought in vain. To know them both demands a change, not of technology, but nature's laws. As though this seems unfair and monstrous strange, this is impossible. Its strictures pause, now and forever, roots to scale the top of our ambition, with a compulsive greed to know it all. Instead, they make us swap what we may know of place with that of speed. These two are tangled. We can pick just one. As with their lovers' WhatsApps and their trust. Arrange it how you like, but when all's done, speed or position blurs. For those who must know one for certain, surely lose the other. Right, so the uncertainty principle is at the core of quantum mechanics, and it's at the core of the harmonic oscillator, and it's at the core of the vacuum of the harmonic oscillator. And as we will see later in this talk, the vacuum of the harmonic oscillator is key to the origin of structure in the universe. Right. But the first thing I want to do is to kind of explain where particles come from. Indeed, explain to you what is a particle. And in terms of secondary quantum mechanics, the bit I want to pick out from this, is that in secondary quantum mechanics you will recall you learn about ladder operators. So you have the ground state of the harmonic oscillator, and you have, which is labeled 0, so this is E, it's H bar omega over 2. And then you also have the first excited state, which you can get at with the raising operator, and this has an energy 1 plus a half. So you can associate it to the harmonic oscillator, as well as the ground state, there are the excited states, and you can get to the excited states through raising operators. Right, now we move on to particles, and the question of what is a particle? There are lots of particles, so I'll focus on one of the simplest ones. What is a photon? You have probably been aware for a very long time that light, or electromagnetism, that light is a wave. You probably learned this at some form when you were in primary school. So light is a wave. Having grown up a bit, you might be able to expand that statement to the electromagnetic field will satisfy the wave equation. And we can write this in did this in various ways, but what I want to and for those of you, which is probably most people outside the first year maybe, who are happy with describing the electromagnetic fields, who are happy with describing the electromagnetic field in terms of the vector potential, I will also write it in this form. But okay, so I hope you've all seen the wave equation, and you know that electromagnetic is a wave, and so electromagnetic fields satisfy the wave equation. What has this got to do with the harmonic oscillator? What has this got to do with the quantum harmonic oscillator? So you're now going to get my the fast introduction to quantum field theory, which skips various subtleties, but is basically correct and basically captures it. Right. So you have the wave equation. So you have this is a classical wave equation. So you look and say, what are the types of solution of this classical wave equation? So you expand the electric field you expand the electric field in Fourier modes. If you are perhaps in the first year and you haven't seen Fourier series, if so, just think of it as expanding in harmonics. Just in terms of like looking at one for each particular frequency and wave number at the same time. So I will write a mu of x of t as, you could do it as an integral, but I'm going to do it as a sum just to kind of, the integrals are more like, if I write it as a sum, pretty strictly it should be integral, but it's easier to write it this way. And then, if I write it this way, then hopefully the physics will be clear. So I just write it as a sum over modes, different modes. Okay? And so you've got each particular mode, and you've got a particular polarization vector for each mode. And you say, this can have an amplitude, so this can, let me write it like this. Okay? So what we have is we're expanding it in terms of waves, and we're saying what is the amplitude of this wave. And what I want to look at is the dynamics, the equation satisfied by this. So we use the wave equation, we put this into the wave equation. The del squared, this gets hit by del squared. This gets hit by 1 over c squared d2 by dt squared. And what we get is that the wave equation becomes minus, so sum over k. So we have minus k squared a minus 1 over c squared a mu double dot. And we require this to be equal to 0. And so the way this has to be satisfied the way this has to be satisfied is that this requires this thing to be equal to 0. And what we get is that for this, the particular coefficient of the in the expansion right, and this is all written up in big block capitals because it's important, and if you weren't following the equation, this is the key result. This is the result I want to, this is the important result I wanted to get to here. So what is the statement? The statement is that if you have something like electromagnetism, which is a wave, it satisfies the wave equation, you expand it in terms of its Fourier modes, or its wave numbers if you like. The amplitude of those wave numbers satisfy a harmonic oscillator. Their dynamics is driven by that of the harmonic oscillator. This is probably familiar to you, even if you're not thinking of it like this. This is probably familiar to you that you have, you know, the waves have like an e to the I omega t, and e to the I omega t is the solution of harmonic oscillators. So the point to kind of put it in this form is that if you say what the classical dynamics of, if you've got something like electromagnetism in vacuum, the classical dynamics of the electromagnetic field in vacuum, or electromagnetism in vacuum, is the dynamics of an infinite number of harmonic oscillators, one harmonic oscillator for each of the wave numbers of the field. So for each wave vector k, there is a harmonic oscillator. Right. Now, we go to quantum mechanics, and we go to quantum field theory. So, quantum field theory is one of these expressions which sounds really scary. Sounds scary? Okay. Okay, it sounds scary, but what quantum field, the physics of quantum field theory, is just promote these infinite number of classical harmonic oscillators to quantum harmonic oscillators. So the physics is that we're going to take these infinite number of classical harmonic oscillators, and we're going to promote them so that they become quantum harmonic oscillators. And we then say, what is the physics of having all these quantum harmonic oscillators? Let me ask you this. The quantum harmonic oscillator that you studied in A3, the basic quantum harmonic oscillator, has a ground state energy. we now have an infinite number of quantum harmonic oscillators. What is the significance of the ground state energy now? It's infinite, yeah. And what you actually have here is the biggest kind of open problem in physics, which is that there appears to be, you would expect in quantum mechanics, that the vacuum state, the ground state, seems to have almost an infinite amount of energy associated to it, associated to the energy, the constant energy of each of these harmonic oscillators. And you may know that the measure of what the energy, the vacuum energy of the universe is utterly tiny, 10 to the minus 3 electron volts to the 4th power. And we know, there is something that we're missing in our understanding of physics in terms of what exactly has happened, why the energy we measure in the universe today, whether there's some dynamic adjustment, exactly what's happened, where all that ground state energy has gone. But there is one thing, but lots of this stuff we do understand very well, and one of the things we understand very well is what a particle is. So, quantum harmonic oscillators, have ground states and they have excited states. So we have an infinite number, so in electromagnetism, we have an infinite number of quantum harmonic oscillators, one for each wave vector. Okay. If you are in the second year and above, you will have learned the spectrum of the quantum harmonic oscillator that you have written there. You have a ground state, and you have the first excited state of the harmonic oscillator, which has an energy of h bar omega over 2 plus h bar omega, where omega is the frequency associated with the harmonic oscillator. And classical electromagnetism gives you then an infinite number of quantum harmonic oscillators, one for each wave vector, and classically, each of these harmonic oscillators has a frequency. Omega is Ck, or I can see as modulus of K there. What happens then when we propose quantum mechanics? The vacuum state has every one of these harmonic oscillators in the ground state. What about the first excited state? So the first excited state is we excite one of these harmonic oscillators. So let me write it as K, and we act on the vacuum, and we go to the first excited state for the quantum harmonic oscillator corresponding to the wave vector K. What is the name of this first excited state? This is a photon. This is a photon. This is a photon with wave number K. An individual photon, we understand this is the first excited state of a harmonic oscillator corresponding to the modes of the field, the electromagnetic field, in wave number k. And this is the modern understanding of particles. And this is supported in an enormous number of ways, and this is correct. That what particles are is that particles are excited states of harmonic oscillators. The first excited state of, you take a field, like an electromagnetic field, you expand it out, do a Fourier expansion of it, and its dynamics are that of an infinite number of harmonic oscillators. The first excited state, each harmonic oscillator corresponds to a wave number. Promote these to quantum harmonic oscillators. The first excited state is a state with one photon of that wave number. The second excited state is one with two photons of that wave number, and so on. This is what particles are. Right. So that is one piece of deep physics. The other piece of deep physics I want to kind of go on to use is the origin of structure in the universe. And those of you who attend my quantum lectures know that I tend to put culture breaks in the middle. And having said what a particle is, I think that's an appropriate time to sort of pause. You know, so let me come to what's one of the big questions of cosmology. So you know kind of the history of astronomy, people have looked at the sky, looked at telescopes, got better and better telescopes, and looked out further in all directions. See, you look to all the ends of the universe, and as this was done, they crystallised from the big questions of cosmology. Decades of observation were turned to catalogues of where and what, with which the curious of every nation considered what was known and what was not. Reflecting on those darkling years, immersed in nightly peep and stare, these seekers reckoned that two great questions were in play. The first, how could the cosmos be so large? The second, how come it looks so much the same? For northern astronomers, eyes tight to telescopes, saw space sweep pearls of galaxies, far more than they could enumerate. Those isotopes they saw, they recognised from Earth. The stars, slot inside our Milky Way. The sight contained familiar spectra, magnetars, as cold white dwarfs and hot red giants. This light had travelled for 10 billion years, so great a journey to encounter charted friends. Why does our local cosmos replicate the physics of its first northern ends? To north and south, to east and west, as far back in the past as eyes can see, the same objects are found, a fact which seems bizarre when you reflect on it. So one of the two big questions of cosmology are, why is the universe look? Is the universe the same in all directions? And why whichever direction it is. The universe is homogeneous and it's isotropic on large scales. And coupled to that is the fact that even though the universe is homogeneous and isotropic, it is not perfectly homogeneous, and it is not perfectly isotropic. It has interesting structures in it, like us, for example. But also, like the stars, like galaxies. The universe has structure. The structure has formed in the universe. And you may know that the structure can be seen in the cosmic microwave background, the light which reaches us from about 380,000 years after the Big Bang, which has perturbations in it at the level of 1 part in 100,000. These perturbations grew and grew and grew. Gravity attracts. Gravity is kind of the ultimate capitalist force, because stuff which starts a little bit just gets more and more and more. And the bits that kind of have less matter to start with they lose that which they were in. And so eventually, with gravity, the place which started with a little bit more gets everything, and the place which started with a little bit less gets nothing at all. So gravity is the uber catalyst. But one of the questions is where did the structure first come from in the universe? And there's two parts we need to put together for this. So one is the cosmic theory of inflation, and the other part is the quantum vacuum. Which is harmonic oscillators. Again. So the theory of inflation is something that comes out of this. I'm going to just describe it. I'm going to go into a bit more detail on how the role of the quantum vacuum. The inflation I'm just going to describe it. The same. So in Einstein's theory of general relativity, both space and time are dynamical. So in Einstein's theory of space and time are dynamical. And in particular, the space can go. So the people sometimes talk about it like the surface of imagine blowing up a balloon, imagine one balloon, something. There's just more space there. The space can kind of grow. Space can sort of stretch. If you've got energy in your space can stretch. The universe just gets bigger. It's not the sort of it doesn't expand into anything. What happens is it just grows. There's just more space. And this in particular is true in the period of inflation, which we think happened in the very early universe. This was a time of majesty. A time when vacuum, empty space, was tightly packed with energy. For in this paradigm, although the infinite cosmos may have lacked electrons, photons, and or normal matter, it had itself. And in itself, it found strength, at first to flex, and then to shatter those geometric chains shackled round its reach and held it small. Not from outside, not through external help or human aid, but from its own reserves it amplified itself. As space divided, more was made to fill the gaps, like sourdough starter yeast, whose spoonfuls have infused by 1,000 loaves and made each rise in zest, but has not ceased to be. Its youth regenerates, it grows and bubbles out, convulsed with potency, alert and dynamic. Such are the laws of space and general relativity. They bear the marks of Albert Einstein's. So inflation is one of the striking consequences of Einstein's theory of relativity. And in it, space grows enormously. So in the ordinary Big Bang, as the universe grows, the size of the universe grows parallel with time. R3 grows at something like t to the 1/2. In inflation, the universe grows exponentially fast. So don't worry what h is. H is called the Hubble scale. Don't really worry about it. Just focus on that. It grows exponentially fast. So the scale of the universe during inflation grows exponentially fast. The universe gets bigger, bigger, and bigger, and bigger, and bigger, extraordinarily quickly. During the time scale of maybe a billionth of a billionth of a billionth of a second, something like that, the universe could have expanded by a factor of something like 10 to the 30 or something. It's, as far as we know, it is the fastest, most rapid rate of growth the universe has ever had. And really, you cannot really compare it. It's very hard to compare to have a proper human intuition to this. When folding paper many times, one sheet to book counts 8 and stop. Try if you must. A further 12 would read past 100 feet. An extra 30 reach the lunar dust. From bedtime tales, recall the Shah who gave 1 grain of rice today, with 2 tomorrow, then 4, then 8, for 60 days. A grave mistake. The Nabob king learned to his sorrow this promise had committed all his wealth and warm sides, enough to drown his land 5 meters deep in rice. This tale itself is short, but tenfold must we understand how much it undershoots what nature did. How faster, higher, stronger was the push of space-time out and through itself. Growth such as ours would turn a penny stock to Google riches worth a Google pound before one tick of an atomic clock could tickle the ears which hear atomic sound. So this is the fastest growth there's ever been in the universe. What is striking about it, what is amazing, is that this growth also results in the origin of structure in the universe. And this, again, comes back to the physics of quantum mechanics. And so this is a story of how the vacuum turns into stuff. How you go from a vacuum state with nothing in it to a state with matter in it. So we come back now to the physics of the harmonic oscillator, and we go back to what is a sort of reasonably standard type of question in second year, it's something like second year, third quarter. So we have the harmonic oscillator. Here's your harmonic oscillator potential. And you're told you are in the ground state of the quantum harmonic oscillator. And then the question goes, suppose there is a very sudden change to, say, the tension of the harmonic oscillator to the spring constant K. Suppose we rapidly, say, change K to K prime, which is very much less than K. So all of a sudden, what happens is that you very rapidly do a fast and instantaneous transition in the spring constant. So that the potential now goes to something like this. So we started with the old potential. So we started with this potential, and that's a half kx squared, and then we go to a half k prime kx squared. Now the point is, and if you've done further quantum, you're probably kind of familiar with what's about to happen, is that the wave function hasn't got time to change. So the wave function has no time to respond. If you do this change very rapidly, the wave function remains the wave function. And so because the wave function remains the same, but the actual ground state of the new harmonic oscillator is not the same ground state of the old harmonic oscillator. So what happens is that the old ground state with wave number k is not equal to the new ground state with wave number k prime. And in fact, the old ground state is now going to be a sum over various of the excited states. It will include the ground state, but it will also include the excited states of the new harmonic oscillator. So a sudden change k to k prime very much less than k, what happens is the quantum harmonic oscillator, it goes from the ground state to a superposition of excited states. Your old harmonic oscillator hasn't got time, the waveform hasn't got time to react quickly, so what happens when you suddenly change k to k prime is that you now used to be in the ground state, but you now find yourself in a superposition of excited states. Remember that I said earlier that when we think about quantum field theory and we think about vacuum, the ground state is one with no particles, and whereas the excited states are ones, well, that's what particles are. When an excited state of these field harmonic oscillators, then you have particles. Right, so now let's go back to trying to put together inflation, starting with and the vacuum, and the origin of structure in the universe. So when the universe expands rapidly, wavelengths redshift. You probably know this through astronomy, the idea that if you look at spectral lines, you look at distant galaxies, they're all redshifted relative to what they are in their own frame, in their ground state, when they're emitted. When the universe expands super fast, as it does during inflation, wavelengths the wavelengths redshift very, very fast. This is not an adiabatic transition. This is an extremely rapid transition. So what happens? So just I'm going to put this all together. So we had quantum harmonic oscillators. What I said that the vacuum of space you have to fill is filled with an infinite number of quantum harmonic oscillators. And then what I've said over here is that if you take your ordinary quantum harmonic oscillator from second year quantum and you suddenly reduce the wave number, reduce k, your original ground state then becomes an excited state of the new harmonic oscillator. So you start with a vacuum state and inflation. Inflation is an infinite number of quantum harmonic oscillators. That's the vacuum. The vacuum has an infinite number of quantum harmonic oscillators. The inflation is the very fastest expansion. Takes k to k prime very much. All the way once you take it to k prime very much less than k. The vacuum becomes a non-vacuum, let me just put it that way, with excited matter in. This is a lovely and beautiful and subtle fact of how quantum field theory works in expanding spacetimes. The vacuum state in such spacetimes transition it all and it turns to a non-vacuum state. Haven't got time to elaborate on this, but just as a side comment, this is also how you understand Hawking radiation. So Hawking radiation you understand the same way. It's the idea that as you take the vacuum of the quantum field of the vacuum and you propagate it through the black hole spacetime, because of all kinds of weird stuff happens with acceleration, the vacuum state turns into a non-vacuum state, The non-vacuum state has particles in, and those particles you can understand as the particles that are given off in Hawking radiation from planets. And this is then structure, and this puts structure in the universe. And this is where we think the origin of structure in the universe comes from. It's as the vacuum state under inflation, the vacuum of quantum mechanics, the vacuum of non-quantum states turn into non-vacuum states, which have got stuff in, they've got matter in, and that is our best understanding of the original seeds in the universe, of where the galaxies came from, where structure came from, and where that 1 part in 10 to the 5 of original inhomogeneity comes from in the universe. So gripped by space-time's device, the small was forced to grow. All childish ties in the neighbourhood were torn, bound to this geometric path which flows up, above and out. And thus was born our quantum universe. Nothing can flee the great expansion. Every fluctuation was swollen huge, then etched indelibly across the cosmos. In this way, inflation picks up the traces of quantum land, whose laws govern the smaller scales, and stretches it from space-time's rack, to set the primal cause of all the magic nighttime skies in it. Inflation is the theory of structure of the universe. It's an inflation which roughly the theory traced dates from my lifetimes. It was first written down in the early 1980s, and it's been gradually understood better since, and then with a lot of predictions confirmed by the cosmic microwave telescopes, background telescopes of the last 20 years. We still don't understand what actually ultimately lay behind inflation, what caused inflation in the first place. We want those plans to trace the inner rationale, sensed but not seen, that drove the stark and adamantine grace of this eternal cosmic growth machine, where raw ingredient of quantum vacuum was taken in at tiness. This fizzes with correlation in the feisty womb of nothingness. The cosmic ratchet whizzes these up and out to ever larger scales, outside the quantum realm, to freeze them in as they turn classical. Each wave entails one more, and constant growth whose origin was empty space plus vacuum energy. Thus bloomed our cosmic home, whose perturbations provide the modern macro legacy of ancient micro-quantum fluctuations. So inflation is the origin structure of the universe. We do not understand anything about it. We do not understand what originally came before it. But fortunately, there are lots of bright young physicists, such as you, learning the subject now, who can answer all the questions that we're currently solving. So, thank you.
So I would like to thank Professor for such an amazing talk, and now I'd like to know if any of you guys have any questions about the talk.
Hi, I would like to ask about symmetry in this problem. So the example you gave has reflectional symmetry, and the new state preserves that because the new conditions preserve it. For the universe, if this initial state is directionally and translationally symmetric, you can't even make decoherence branches if you don't have some kind of symmetry breaking, surely. So the question.
So yeah, so we have so we have Lorentz symmetry. So with the universe, we think at the smallest level we've got the Lorentz symmetry. What happens with with inflation is that the kind of way to express it is that it leads to the fluctuations it leads to. So in terms of kind of like they'll kind of what we call scale of you did an expansion one concern. They'll kind of like they'll scale of fluctuations. So they've got kind of mod amplitude squared, and these kind of maps. So there isn't a preferred direction to them. They don't come out with a preferred direction, but they kind of come out with an amplitude. So you have you have there isn't any preferred direction in the CFD or where these things. So the universe has its properties of homogeneity on large scales. It still has homogeneity. It has isotropy. But what you have got is kind of like amplitudes of perturbations, which are kind of technically in a kind of cosmological perturbation theory language, they are kind of scalar perturbations.
Anyone else?
This is maybe a bit of a simple question, but I was just curious. So you've gone from your T and V there, your Hamiltonian, and you've quantized it. I was just curious. You could come up with like a different formulation of that Hamiltonian. I don't know. You could factor it, for example, in some way. And obviously, that quantization process is you could come up with many quantum theories for like the same classical theory. They would correspond to the same classical theory, but the operator structure would be different. How do you decide how to do that? Because, for example, you could resolve the zero-point energy problem there if you chose a slightly different ordering.
So the way, okay, so the first one, I think the quantization language, I think is always the wrong way to think about it. Because quantization language has this idea that the world is classical, and really you should start with classical theories and then turn them into quantum theories. Whereas really the world is quantum. You know, the world is quantum, you should start with quantum theories, and then. Right. So particularly with the harmonic oscillator, the harmonic oscillator is always one of the simplest quantum theories. You just started from the quantum language. It's always one of the simplest theories you can possibly write down. You can't really dodge the zero-point energy. And the reason is that even if you think you could by just say, oh, I adjust the origin of what I call zero, because it's h bar omega over 2. Now, if you have a single harmonic oscillator like you have, then you could just dodge it. But the thing with the electromagnetic field is omega is different for every mode of electromagnetism. So there's a different omega for every mode of electromagnetism. So there's no one choice you can ever take that will just remove the zero-point energy problem with your quantization.
So you said for cosmic inflation that you'd expect particles to be created because of that. Would you, for other types of inflation, say in an Einstein-persistent universe, would that also create particles, or do you need a certain rate of expansion to start creating particles?
Yeah, so any time, whenever you have acceleration in general relativity, whenever you do kind of a quantum field theory with acceleration, you always have effective basically particle operation. So that's the physics of inflation. That's the physics of Hawking radiation, and there's also something called like a Rindler temperature. So this is even if you're in completely flat space-time, you get your rocket and you press accelerate on your rocket. Then in quantum field theory, actually, what will actually happen? I think in the real world, what will happen is you will see an effective bath of particles that are actually coming towards you, even though you started in a vacuum with nothing in it. When you start accelerating in your rocket, you will actually be feeling as if you're going into a temperature gas at a certain temperature. That's a surprising thing, but that is actually how, and it ties to this thing that when you start accelerating, what was your old vacuum with no particles is not in your new frame, is no longer a vacuum state. It's got particles.
So you mentioned that the vacuum can be modeled as a collection of quantum harmonic oscillators. And so, what are the typical separations between two harmonic oscillators in this case?
So, one way you can kind of think, you could think of it. Okay, so let me give an analogy. So you could do something similar to what I've done, where when you looked with the physics of condensed matter and atoms, you could do something similar, where you kind of think where you've got wave modes, and these are associated, you've got like phonons, and these are associated to matter. And then you've got like a finite scale, because you've got the scale of atoms that cuts you off. So then your theory looks like a field theory, but then it gets cut off at a length scale of the atomic separation of about 10 to the minus 10 meters. With the particle model, with space-time, in principle, there is no, modes go down to arbitrarily high resolution. So in terms of frequency, you can go up to arbitrarily high frequencies. On the way we treat this. This ties to then fundamentally some kind of quantum gravity theory will cut you off at the highest energies. But if you just do normal, simple quantum field theory of electromagnetism, quantum electrodynamics, you have an infinite number of harmonic oscillators, which are, if you like, infinitely close together. Yeah. And I will say that all the things that make quantum field theory hard are dealing with these infinities. Yeah, that's the thing that makes quantum field theory hard, is how you deal with the fact that these infinities, because naively every calculation you do gives you an answer that's infinity.
So does this way of looking at it suggest that an equal amount of particles and antiparticles would be created? And then if so, where would the asymmetry come from?
Yeah, so that's a great question. So this is like, you would then think, well, what process can lead to a difference in the number of particles and antiparticles in the universe? Yeah, and so this is called the baryon symmetry problem. There are various conditions on like what would happen, how can this happen? So these are called the Sakharov conditions, named after the Russian physicist Andrei Sakharov. And basically, they involve you have to be out of thermal equilibrium, you have to be out of equilibrium in various ways in order to generate a difference in particles and antiparticles. If the universe was always in thermal equilibrium, you could never generate a difference in the number of particles and antiparticles.
This might be a bit of a silly question because I don't think I understood some of the stuff that went on towards the end. Maybe it's just beyond the scope of what we're discussing here. But I don't understand how like inflation allows us to go from a homogeneous and ice-struck universe to one that's not, or even one that's locally not. Because I can imagine how even a little bit of non-homogeneity would allow stars and planets etc. to form. But how do we even end up with that tiny bit of non-homogeneity?
Right. So yes. Okay. So the bit that is the kind of thing is that so you started with basically everything in the vacuum, and that's just completely homogeneous. Then as you come out of then what inflation does is because it's changing all the wave numbers, what used to be your vacuum state is then for each of these wave numbers, it's no longer in the vacuum state. Okay. So what you then have is you have like a superposition of states, and then this has to classicalize. So this has to then this wave function collapses as you were, if you like, according to particular cases of this, and that's a probabilistic collapse. So given you're not in the vacuum, then you've got a probabilistic collapse to an actual from a kind of coherent quantum state to a classical state. As you end up with your not vacuum state, because it's a not vacuum state, it's not perfectly homogeneous. It's still almost homogeneous. It's homogeneous to 1 part in 100,000, and why it's 1 part in 100,000, that's where the calculations come from. But that's why it's not perfectly homogeneous. We're giving you starting with something that was perfectly homogeneous.
What happens if we increase the spring constant rather than decreasing it?
So in principle, it's the same thing because if you do it fast, then you're no longer in the vacuum state. So you're now moving to an excited state.
I was thinking like, the ground state of the new spring constant might be more than the energy we start with. So don't we end up with energy that is less than the ground state?
So once you're in your new system, almost by definition, whatever state you have, when you expand it in states in the new system, will be some linear combination of all the states. And as long as it's not precisely the ground state, then it has to be ground state plus excited states.
About 3 questions ago, you were asked about the conditions for forming matter, and I think you said that the universe has to be out of thermal equilibrium.
Yeah.
But what would it be out of equilibrium with?
So itself. So for example, one way you can be out of thermal equilibrium is if you have phase transition. So if you're cooling down, say if you've got you're cooling down water to ice or something, and what happens is certain bits of ice are nucleated first, and while you've got water water elsewhere. So you could then have a thing where during the phase transition, you are not in perfectly. Yes, you go out and you think everything is smooth everywhere. So phase transitions are one of the cleanest ways to get out of everything.
Do we have any more questions? So I think we are done. I would like to thank Professor Conlon for this talk and a round of applause.
And if anyone wants a copy of my book, £10 cash.
The pizza will be arriving in 5 minutes, so yeah, if you'd like to chat, ask questions, wait in the reception, yeah, please go ahead. Thank you.